so the two primitives that we would possibly use is as follows. One was this thing that I told you at the very beginning, that in a geometric series it is the last term that dominates. Let us look at another problem. Say you have a convex polygon and you have a point outside. What I want is to compute, pardon my drawing, there can be two tangents from this point to this convex polygon, right. What is the definition of a tangent? A line going through this point P. So, this is a convex polygon P of n points, so given to you in some order, right, in circular or counterclockwise, clockwise or counterclockwise order, and given a point P, I have to figure out the tangents to this convex polygon. So, what is the definition of a tangent? That if you draw this line, it hits the polygon at a point and all points lie on one side. So, there will be 2 points, 2 such tangents, fine. What is your hunch? How much time would you take to compute such tangents? So, essentially see, I mean, for any point in here, if you draw this line, there would be some point above, some point below, but these 2 points has a specific nature that all points lie on one side. So, linear possibly you can, but in the exercises which I think Gopi will do in today's tutorial is you can do it as fast as this. The idea is binary search in a nice fashion. It is not a very pretty obvious, but see, the point is, if you compute the distances or angles to all points, then you cannot escape order n, right. So, that means, if you are targeting for a log n kind of thing, you cannot do explicit computations at all points, right, because if you do explicit computations at all points, each one will take constant amount of time for a total of order n time. So, that means, you cannot do explicit computations at all points, you can do computations only at log n many, order log n many places, right. So, we will assume that there no log n. So, the problem is P is given to you say in a counterclockwise order or a clockwise order, right. So, P is given to you in this order, the points of P are given to you in this order. So, starting from say P 1, P 2, so on and so forth, right. Now, the problem is you are given a point, right. So, point outside, you know what is the tangent. So, compute the tangents from the point P to this convex polygon. P is a convex polygon, remember. So, your input is a convex polygon P of n points and a point P. Your output should be the 2 tangents from P to capital P. The challenge is to do it in order log n, right. So, that is what I said, we will do it in today's tutorial. As of now, assume there is a black box which can solve this problem for me in log n amount of time. Okay. So, I do not give you the proof just now, we will do it in tutorial, but for now believe that given a convex polygon in an order, in a clockwise or counterclockwise order and a point P, I can compute these 2 tangents in order log n time. The only thing you should appreciate is, if I have to do it in log n, I cannot do the computation at all points of this polygon, right. I have to, I mean, what is the idea of binary search? You discard, so if you are wanting a base of 2, then at each step of the iteration you discard half of the points. That should be your idea. So, as because this is given in order, so you have to discard half of the polygonal points in each iteration, right? Fine. So, these are the two ideas that I would use, that you can compute these tangents in log n time and this idea of geometric series. Okay. Let us now go forward with this to knowledge. We make even a very strong assumption. Say an oracle or someone has told us the value of h. Fine. Now, see, we can, if someone has told us the value of h, can we do something to get the convex hull in n log h time? Fine. So, the idea is as follows. So, I group these points arbitrarily, so that each has h many points. Fine. Because someone has told me h, right. So, each one of these groups have h points. So, how many groups do you have? So, the point set P has n points. Okay. So, I have n points. So, the number of groups is n by h. Assume that this is an integer, right. Otherwise, we will have some many less than h many points in another group.
So, in the intersection there may be some points
yes.
That will be counted as
no. So I make a partition. It can be anything, right. Just arbitrarily partition. So, for your first partition, take the first h points. Okay. Next take. So, they may look anything arbitrary.
so that is your
Yes. The only thing is each group has, right, because otherwise I could not have written this n by h groups, right. So, it is a partition of P, where each partition has h many points. Clear? There are n by h many groups. Yeah.
So, there is no point repeated in that group.
No. I said, that is what I said. It is a partition. So, a way can be pick up the first h points. This is your first group. Fine. Pick up the next h points. This is your second group. but no point is repeated. So, that is the reason the number of groups is n by h, and assume n by h is an integer. Otherwise, you have to deal with floors, ceilings, you can do that, but that would get a little bit nasty, I mean, right. So, just assume that n by h is an integer. Now, what I do is, so for each group compute the convex hull, right. So, see these are the, think of them as your convex hulls. See, points are not repeated, but the convex hulls may overlap, right. The convex hulls may overlap, fine. So, to compute the convex hull, let me even make a little bit, maybe compute the convex hull using, sorry, using Graham scan, right. So, computing the convex hull for each group is order h log h, right. How many groups? N by h. So, in total we take n by h groups, for each group you take h log h. So, this is order n log h, agreed. So, in n log h time I have computed all these small convex hulls, each having h point. Okay. Now,
What is the relationship between this order of n log h and geometric series order of r?
we will come to that, we will come to that. So, keep that in the background of your mind, these two things. Okay. Next, I start with a point of which I am sure to be on the convex hull, the leftmost x coordinate of all points, right. This is kind of we have convinced ourselves that that is always going to lie on the convex. Right? Now, what I do is, from this point I draw tangents to all this rest of them, right. I just invoke does it take some time to shift if I click here? No? Yeah. So, I will invoke this, fine. No, a point of which I was sure, the leftmost extreme point, right. Okay. So, let us shift. So, So, what I did was, starting from this leftmost point, I drew tangents, right. Now, each tangent drawing operation would take me how much time? Log h, because there can be at most h points on each one of these small groups. Okay. So, tangent to each convex polygon takes order log h. So, kind of this black box has given for me. So, how many tangents do we draw? N by h order, right. Fine. So, for a total of n by h log h, right. So, in this amount of time, I have been able to draw all these tangents, and again as in Jarvis March, I can figure out an extreme slope, right, that should take me to a next point of which I am sure that it is on the convex hull, because this line segment has everything on its one side. Done. So, I have come here. Fine. Again I do the same thing. So, from here you will jump to another polygon. Again, so you do the same thing. Again you draw all these tangents, right. Again take the minimum, you get one extremity, you jump to another polygon, again you do the same thing. Now, you keep doing, keep doing, keep doing. How many times do you need to do it? H times, right. Now, let us go back to that computation. This complexity was for one drawing, and you know that there are h points on the hull. So, you multiply this with a h. So, as because someone has told you h, so after doing, so this was your first computation, then you came here, then you went there, then you went there, then you went there. So, there will be only h many computations, right, because h is the number of points on the hull. So, after having done h such computations, you will surely wrap back to where you started from, and I am done, right. So, add this n log h with the earlier n log h. So, for a total of order n log h. The only problem is nothing comes in life for free. No one is going to tell you that h. So, what I will try to do is, I will try to estimate h. And how fast I can estimate, on that everything hinges. Now, for that I will go back to this idea of geometric series. So, we understand that this is what is going to dominate. Okay. Now, what I do is as follows. I start with an estimate of, so the minimum h can be is 3, right. So, I start with an estimate of 3, and then I can check 4, then I can check 5, I can go up to h can be at most n. So, I can check for all of these values, right, but then this n log h should be multiplied by n, you are going to n square log h. So, what should I do? So, this is my real line. So, here is 3, here is n, and somewhere in between there is this correct h. I do not know this h and I have to estimate it. But mind one thing, if you work with a smaller estimate of h, of the correct h, then when you do this algorithm, say your h was 15 and you estimated it to be say 10, then surely you will not wrap back to where you started from, right. But say your correct h is 15 and your estimate was 20, then surely you will wrap back there, and you know that you keep in memory the point you started from, then you know that I have reached, right. So, this gives you the clue. I start with 3 and if I make small jumps, then I will take more time. Rather what I do is, I start with 3, I square it, 9, again I square it, 81, right. So, sooner or later I will have some h star and some h star square, in between which I must have trapped h, right. Now, how much is this, right. So, see the rate at which I am growing is, I started with 3, my next thing was 3 square. So, after I steps I will go up to, right, and this 3 to the power of 2 to the power of I and 3 to the power of 2 to the power of I plus 1, in between this I must have trapped my h, right. And now, so see, I mean so this is my h and this is my h star and this is my probably h star square, right. Now, see this is a geometric series. So, it is only the last term that dominates, and if you take its log, what is coming out? Only I, right, and that is your n log h, fine. So, just go back and just do this thing. So, essentially what you are doing is, at each step you are taking n log h, fine. Your h can be maximum 3 to the power of 2 to the power of I plus 1, which is surely greater than your correct h, right. So, your h comes into the complexity. Now, you think of this, if you take h square, this should be greater than, think of h square, this should be greater than your h star square, right. Agree? So, essentially the algorithm is this. The earlier routine which I said, that when you know h is kind of a black box. How many times do you call it? You start with 3, then you call it with an estimate of 9, then you call it with an estimate of 81, right, that is 3 to the 4, then you call it with 3 to the 16, keep going, and sooner or later, mind you, the moment you have crossed h, then you will surely wrap back, right. So, essentially now you are looking at, so this algebra you have to little bit do, you are looking at n log of 3 to the power of 2 to the power of I plus 1, right. This is the series that you are looking at. And you have to do this algebra a little bit correctly to convince yourself that this is like n log h.
Finding that I is also very important.
No, see, this I will come via the algorithm, right? How? So, understand the algorithm first. The algebra is not much there to say. The crucial idea was, if my estimate is below h, then I will not wrap around, right. But if my estimate is, if I overestimate, then I will surely wrap around to the correct point, and I have got my convex hull.
So from there one can determine the
Right. And this 3 to the power of, now if you now look into this,
So mainly I am interested in lower I, smaller I will be that is
yes, and that is the reason you square, because if you are, see, squaring, what it does, it allows you to make bigger jumps. But if you are doing smaller jumps, then you would have not possibly got log h. So, the sum would be like, to sum k such that this 3 to the power of 2 to the power of k plus 1 is less than h square, fine, and then your algebra follows. So, what I suggest is, I will be here around today evening, just do this algebra, right. There is nothing much in there. The idea, once you have understood the idea, just do this. So, the idea is, this k should be such that 3 to the power of 2 to the power of k plus 1 is below h square and greater than h, right. Surely within that, this h star square is there. Got it? Yeah. So, then you are doing log n kind of thing. This is even less. Your dependence, I have to make it dependent on h, right. So, then you will have kind of log n thing. My idea is to get to h. That is why you see, I mean, whatever I am playing around with has something to do with h, because I stop the moment. So, all my computation for estimates of h which are below the correct estimate of h, I have done the computation. There is only one computation I do when I have done an overestimate, because then I know that I will surely wrap back. I stop there, right. So, now this everything, every algebra depends on h only. So, essentially if you look at this, it would look like sum n to the power of this sum. This would be a geometric series, right. So, do this today evening. If you have any difficulty in understanding, I will be around here tomorrow, ask me, right. As I said, this algebra just follows nothing but this one, that only the last thing dominates, right. So, only that computation which I did by overshooting the correct value of h, that is only that matters, right. The rest terms do not dominate asymptote. Any queries? Yeah.
I can start from 0, or is there some specific value with that I should start?
So, 3, because your lowest convex hull size can be 3, right.
3 is not I value, 3 is like total value. I should start with like what value, 0 or
No, see, I started by saying that someone has given you the estimate of h and then everything was correct. Now, what I am trying to do is I am trying to estimate that h, right. So, the smallest possible estimate of h can be 3, everything within a triangle. So, with that I do this algorithm. If it wraps back, then I know that I have found my correct hull, right. If it has wrapped back to the point from where it started, right, say it does not, then I know 3 is not a correct estimate, right. Then I increase my estimate value, right. I now make a little bit bigger jumps, 3, next I see 3 square. So, each time I square the estimate, 3, 9, 81, so on and so forth, and sooner or later I will get 2 values within which I can trap h, and so my complexity would now depend only on, but I am taking logarithmic, right. The h thing is within the logarithmic, right. So, that is why this 2 to the power of I comes down, right. Right. No, no, I need not. That is what I said. See, my estimate is, so say for example, I am operating on 9 and 81, right. I checked with 9, I did not wrap around. So, I know that my H is greater than 9. Okay. Now, I start with 81, I do all this stuff with 81 and say my correct H is 40. Now, after having done 40 computations, I surely should come back here, right. I appreciate this fact, right, but I have done my calculation with 81, not with 40, but still it is going to be n log h, right, because this 40 lies within 9 and 81. You take logs, one is 2, the other is, now you understand. So, it is just just a quick idea of this. Yeah. Think of it. Think over it. This is a good question. Think over it. Then what might happen is, so there is kind of an optimized thing there. You might lose h in the logarithmic. So, someone was telling, right. So, I first do at 0 or at 3, I do at n, right. Now, if you do at n, then you cannot escape n log n, right, you are gone. So, how long a jump you make, that you have to judiciously choose. Now, I gave you the idea of square, but the reason I a square or any constant powering is okay, because what I want is the base of the log to be a constant. Then I can get between two square numbers, trap this h. The range within which I trap h should be within two constant powers of two numbers, right. Then only you can expect a log h there, right. So, you can do this calculation by taking some variable x and see how it goes. Okay. Any more queries? So, what I want you to do is do this calculation, this algebra yourself, and listen to the tutorial today to this. Then I think everything will fall in place. We would try to introduce something which would be useful for some later lectures. So, let us start with a simple problem like this. So, you have n points and your goal is to compute the minimum of P. Okay. So, what is the simple algorithm that you know for computing the minimum? You take the first two numbers, whichever is the minimum, you declare that to be your minimum. Then you compare this with the third number, right. So, at each step what is happening is there are two operations that you do. One is a comparison, the second is a updation, right. But notice a fact that you cannot avoid precisely n minus 1, right. You cannot avoid order n many comparisons. The question is, in the worst case it might be almost the same, at each step you update. That is kind of a very worst case input, right. That will not happen every time. So, let us look at kind of an average behavior of this updations and try to estimate that. Now, look here, first makes a few assumptions that will allow our mathematics to go through easily. Assume that your input is any random permutation of these n numbers, fine. So, it is highly unlikely. Now, see, this worst case will happen when the numbers are in a decreasing order, right. You will have the maximum, but that is only one of the factorial n inputs. This is not going to happen every time, right. So, then what is your hunch that in the expected case, what would be the number of updations? N is a obvious worst case upper bound. What is next hunch? What can be? What can it be? Yes, log n, right. Let us see. Now, see, if I have to analyze this thing, then what happens is I have to argue over all possible permutations of these n numbers, right. So, if I am to do this mathematics not possibly intelligently, but just doing through the calculations, what I should do is I look at all the factorial n many inputs, compute the updations for each one of them and then take a average, right. But that is a very messy, that would be a very messy kind of calculation to handle. Rather we would do something intelligent. What I do is, I define this as the first I points in any random permutation of this n points. Now, what I can do is now condition on this I points, I will try to make an argument on this number of updations. That condition on this fact that this were the first I points, there can be factorial I many of them, I can condition on each one of them. Now, if it so happens that my argument will be the same for all these conditionings, then I can get rid of the conditioning, because it is true for any I then, right. Okay. Now, look into this fact. What I do is, instead of looking at the updations from the forward direction, let me look at it from the backward direction. There will be merits for it. So, this framework is known as backward analysis, and this is a framework which computational geometers keep coming back to again and again when they have to handle randomization in some way. So, there is this framework which Professor Sandeep Sen I think will talk of in the next week, is this framework of randomized incremental construction, where this kind of analysis would be very much needed, but again those would be on complex geometric structures, but here we are in a very easy domain that we can handle. Which one? So, backward analysis is about seeing it from the backward side. Let us talk concrete, you will understand what I mean. Fine. Now, see, my algorithm was in the forward direction, right. So, I first checked this first 2 points, whichever was minimum I updated it, then I checked with the third point, checked with the minimum, if the third point wins over is the minimum, then again I update, keep doing, right. Okay. But tell me, when can there be an updation at the ith instance? If and only if it is the minimum among all of them, right. So, what I now do is, so this is what backward analysis is all about. I have inserted, right. Now, what I do is, I just take off I and see what happens. Instead of arguing from the front, I argue at the back, right. So, for this set capital P I, I have got a minimum, right. Now, I just lift this point P I and try to check if there has been an updation at this instance. There would have been an updation if and only if P I was the minimum among all the points. What is the probability of that? Mind you, I made an assumption all numbers are distinct. So, what is the probability of that? 1 by P I, right? Sorry, 1 by I, good. So, as your I keeps increasing, this probability is decreasing, right. So, now make a so you know how to handle I will come back to this again, just hold on for a moment. So, if there is a random variable x, everyone is comfortable with a random variable, right. What is a random variable? A variable that is random, no? What is a random variable? Right, as sir tells you correctly, a random variable is a function that maps your sample space to say positive reals, fine. So, think of your random variable always as a function, and you can define the expectation of a random variable as that, all of you know, as this, right. Agreed? So, a random variable is a function, attached to it is a probability of the random variable taking. So, this probability P x is the probability that capital X takes this value small x, fine. Okay. There is another property of expectation which is known as linearity of expectations, and this is very useful, that if you have a bunch of random variables, I really do not care about whether finite number of random variables, and I really do not care about their dependence or independence. And if I have a random variable defined as a sum of them, then expectation of x is nothing but their sum of their individual expectations, right. So, this everyone knows, we recollect this. Okay. This is one thing, and for many of our we will deal with 1-0 kind of random variables, right, binary indicator random variables. 1 if some condition holds, like in our case 1 if there is an updation. So, let me tag with it an I, right, x I is equals to 1 if there is an updation at the ith iteration, 0 otherwise. Fine. Now, if I do this, what does it mean? Total number of updations, agreed? Because it is 1 whenever there is an updation. So, you add everything. So, x means the total number of updations, right. Now, you take an expectation over this. This is what I would be interested in, and as because linearity of expectation holds, you can just figure out this and then take the sum. Fine. And as because xi equals xi is an indicator random variable, it takes binary values only, then you can also show that expectation of xi is nothing but probability of, right, because 1 into probability of xi equals to 1 plus 0 into probability of xi equals to 0, that part goes off, you are just left with this. So, if we can, the idea is for this sort of situations in probability, if you can break down your complex problem into smaller binary indicator variables, then just if you can figure out this, you can compute the total expectation, right. And mind you, this is precisely what we did in this case. This was actually our probability of xi equals to 1 that we did. So, what is our final result? So, I need expectation of capital X. So, this is nothing but each one is what? I equals to 1 to n, each one is 1 by I, and this is nothing but a harmonic series, as I would tell you, and asymptotically this goes to, right. So, what was a very messy kind of calculation, if you went from the forward direction, now becomes a neat nice calculation if you do a backward analysis. So, mind you, in the worst case you can still have order n many updates, but this calculation, this mathematical calculation shows us that on the expectation your number of updations would be log n.
If we go from back on most cases, it will be log n.
No, not most cases. See what I have argued. First, what I said, this argument that I was making of 1 by I, this I condition on this set to be your input, right. Now, mind you, whatever your P1, P2, Pi are, in whatever order they come, look into all the factorial I orders of them, this 1 by I is true, right. I repeat, I started by saying that in the worst case you can have your updations can be as much as the comparisons in the worst case, but what we are arguing is on the expected case, right. Now, think of your life situations, right, not the cyclone Phony does not happen every day, right, it is a worst case scenario. So, I am trying to bring in probability by what I did was I fixed these input sizes, right, I conditioned on an I, a set of size I, and I got a property that is independent of any rather it does not depend on the permuted order of these I numbers. So, I can get rid of this condition, right. Now, what I did say that the probability that there will be an updation at the ith step is 1 by I. Why? Because the updation will take place if and only if the minimum number appears at the ith location, else the updation must have happened somewhere earlier. So, so your favorable case is only 1 and your total case is I. So, the probability that it gets updated at the ith step is 1 by I, and then I did this calculation. Right, because I did. So, the x I was like, if there is an updation at the ith iteration, and then then I looked at capital X, which was sum of all x i's. So, what is capital X? It is a random variable, because now I look at all, I attach probabilities with each and every input permutation, right. So, capital X is now all updations when I sum from I equals to 1 to n, right. So, I am looking at the first, second. So, what was my I? Right. So, I increase I. Now, you understand that as you go, you increase the size, your probability of updation is going down, right. Sorry. Yes, the updation will only have, that is the observation that you have, right, that the updation that x I equals to 1, this probability is basically 1 by I, right. So, think of this quantity. What is this quantity? It tells you what is the probability x, what is x I? It is 1 if there is an updation at the ith instance, right, and you have seen that there will be an updation at the ith instance if and only if the ith number is the minimum among all this ith number, right. So, if it is some other number apart from the minimum, then there will be no updations.
Suppose it is sorted, now it is minimum easily. So the idea is that if it is in decreasing order, then the PI will be the minimum.
No, I am arguing on a random input now, right. So, that is what I said. You look at all I factorial permutations of this, but this observation that there will be an updation at the ith instance if and only if that is the smallest, right. So, this is true of all permutations of these I numbers. Your input can be any one of these I permutations. So, I can even get rid of the conditioning. Right, because that's my algorithm is, and mind you, I have not left anything, because I am looking at this sum, right.
Even that also happen for the forward case. Suppose it is smallest happening, random permutation. Suppose
No, you cannot analyze it as easily as this one.
suppose ith element is the smallest one, then that will be updation. Suppose the smallest element is the first element.
No, but then how do you argue probabilistically? So, what I am arguing is there is an updation,
Yeah, if that will be updation, that will be 1.
right. If and if there is an updation, then this number must have been the minimum among all of them, right. This is my argument.
Might not be updated.
Agreed? Yeah. You had some queries. Heads down. Yeah. But this is just bringing in probability. You must have appreciated this fact that there will not be as many updations as comparisons, right, and the mathematics essentially tells you that. Yeah.
So, in that, if you could go to the last view. So, in this PI, we started from back, but as we said that it is just a random sequence. So, instead of starting from back, I can also start from front. So,
No, then you see the updation. So, you have to add everything coming up to this, right. Here I am operating on a conditioning that I have found out the minimum for the first I, right, and then so what I do is I fix it on an I, fine, and I argue that there has been an updation. So, I really can forget about what was there earlier, only looking at the ith instance, I can fix a probability that there was an updation at this instance, right. So, I have inserted the first I numbers and now I look back, right. We can even extend this to sorting. I will not do the analysis, but give you the idea. The idea works as follows. It is kind of a variant of quicksort. So, say you have some n numbers, and I start with this interval. They will be in this real line, right, somewhere, and what I do is I keep from each point a pointer to the interval it belongs to. Fine. So, initially everything points to this, only I have one interval minus infinity to plus infinity. Now, comes say I now take P 1, fine. P 1 will belong somewhere. So, say P 1 belongs somewhere here. Now, what I have done is I have broken up this interval into minus infinity to P 1 and P 1 to plus infinity. So, now these pointers have to go to their correct interval, fine. So, say P 2 goes updated there, say P 3 goes here, P 3 goes here, P n goes here. So, you keep doing this. Again you see take P 2, see, so you now know which interval it belongs to, go there and place it in that interval. Again it will subdivide this interval, again you have to rearrange pointers, right. Okay. So, what I am doing is for this sorting algorithm, for what I am now doing is I have this real line and I have taken say the first I numbers, I will just wind up. So, you have done the first I numbers, right. So, here was possibly your P 1, here was your P 2, here was your P 3, here was your P I. So, you have divided. So, if you have inserted I numbers, you have divided the total interval into I plus 1 intervals, right, and the rest of the numbers are somewhere here. So, these are here, these are there, this is there, this is there, so on and so forth. And also for each interval, so make all these pointers bidirectional, right. So, whenever I have an interval, I can also figure out in the big array which are the numbers that are within this interval, right. If I can pick up a bidirectional pointer, I can do that. So, that means for each interval, I call this list to be the conflict list. So, for each interval, I keep this conflict list, right. So, what I have to do now is, now my work is what? Whenever I say when I am going to insert P I plus 1, I have a pointer knowing which interval it will get into, I place it in there and then I have to do some updations with this pointers. Which pointers only? Conflict list of the interval into which P I goes, right. So, I am looking at P I plus 1 and by this pointer I come to the interval. For this interval I can have this bidirectional pointers having the conflict lists. So, these are the only numbers that will get affected.
Why are you calling the conflict list? Is it that
No, I just this is just a name. So, conflict list for an interval is the numbers in the capital P which lie within this interval, fine. In a sense it is conflicting with the interval, fine. So, the conflict list for an interval are only those numbers which lie within this zone, right. Now, when I have figured out, when so I was kind of randomly inserting. So, when I inserted p I plus 1, I know the interval from this direction of the pointer, the interval to which it will go, right. So, it will lie between this p 3 and p 2. So, it lies somewhere here. Now, my point is only looking at this, if I can reorient the pointers corresponding to this conflict list, then I am done. I need not look into the conflict lists of the intervals to its left, to its right, they will remain as it is. Agreed? You do not seem convinced, white vest. What? You are not convinced, or you have lost track? Lost track, okay. And this is pretty simple, right? These intervals are ordered, right? And for each interval I know the numbers that lie within this from this conflict list. So, I know that these are the only numbers that will get reoriented. Now, again see, if you are a little bit, if you can see a little bit far, this is nothing but the previous case in a little bit complicated way. As you keep going, I am breaking into more intervals, numbers here are reducing. So, the updations as you go more towards the right will sort of reduce, and again this will lead to an n plus kind of a order 1 by I, and this you know to be a harmonic series. This would solve to n log n. This is kind of a randomized quicksort, yes. This is quicksort in a, I mean I stated quicksort in a different way. The reason is as follows. I will not get into the analysis, but now look here. See, I have computed the convex hull. So, now forget numbers, I have points. So, these are my points, right. These are points in R 2. So, what I now do is, for each point outside this convex hull, I take a point inside, right. So, what I did was, this is a incremental construction. So, I took the first 3 points, formed a triangle, and I took its centroid. The first 3 points that came, I computed its triangle and took the centroid. Now, as I keep growing, this centroid can never go outside the convex hull, right, it will stay inside. Now, what I do is, for the other points I always maintain I look at these lines, and these lines will conflict with some edges of the convex hull, right, they will intersect some edges of the convex hull. Now, like in the previous case, I had for an interval, I knew the numbers that are within this interval, and for each number I knew which interval it lied in. So, similarly for convex hull, what I will do is, for each edge I know what are the points that are in conflict, and for each point I know what is the edge it is going to cut to get into this centroid. Again see the same structure, fine. Now, say I pick up randomly one point. So, this is my I plus 1th point. What I do is, I look at the edge it is conflicting with, right. From this bidirectional thing I can figure out the edge it is I look at its 2 end points and I join them. Now, this will not be the correct convex hull if these two corners are concave corners, right. They are concave corners, because this is a concave corner. So, what I do is now I keep pushing this to that side and keep pushing this to this side. Slowly and slowly I will have this tangents. And now, see, this is your this green part and this red part, this is your total convex hull, and all these points that have gone inside, they are not going to reappear again on the convex hull, right. And mind you, once a point is deleted from your convex hull, it is never going to come back. Now, what I have to do? For each edge that is lost, I have to manage their conflict list in a nice way, right. So, for each edge lost, I have to take this conflict list and point it to this new edge that has come, right. So, like this earlier line, so think of this earlier line, right. This was earlier conflicting with such an edge, now it should be reassigned to this edge. Again the same structure and the same analysis, right. So, this is kind of the framework of this randomized incremental construction, and again the analysis would be, it would help you to do a backward analysis for this one, right. So, I have sort of hand waved towards the end, but I think I have possibly given you the feel of it. We have explicitly done this minimum thing, and the rest is like I have given you some ideas. Okay.